okay.
Yeah, sure. Okay, it's very informal. Okay, so I can share my screen, I take it, right?
Sure, yeah. I'll just give you an intro and then we can start. Yeah, you can start sharing the screen.
Okay, so
Okay,
just
so
give me.
it's a great pleasure to have with us Alan Oblitsky. Alan received his BSc degrees in Mathematics and Electrical Engineering from Ben Gurion University in Israel and MSc and PhD degrees from Stanford University. He spent a decade at the Communication Analysis Research Department at Bell Labs and a year at DE Shaw. And soon after, he joined the department at UCSD, where he's currently a professor of electrical and computer engineering and of computer science and engineering. And he holds the Qualcomm chair for information theory and applications. So his research concerns information theory, statistical modeling, machine learning, and focuses on fundamental limits and practical algorithms for extracting knowledge from data. And among several other distinctions, Alan is a recipient of the 2021 Information Theory Society Claude Shannon Award and the co-recipient of the 2017 ICML Best Paper Honorable Mention Award, the 2015 Units Best Paper Award, the 2006 Information Theory Society Paper Award, and the 1992 Paper Award. So thank you, Alan, for making the time and over to you.
Okay, thanks. Thank you very much for the kind introduction. Okay, let's start. Okay, right. Can you see the slide?
No, not very.
You cannot? Just give me 1 second here. Um, just a second. Okay, so now better?
Yeah, now it's better. We can see you.
Okay,
Yeah.
cool. All right, perfect. Okay, cool. Thanks. All right. Okay, so I'm going to talk about some small improvements to LLM English Perplexity. And this is joint work with SN Ergun, who's a student with me, and he's done a lot of work, great work on this. Okay, so basically what we were trying to show is that even though large language models are very big and very foreboding and complex, um, in fact, you can still contribute to them, maybe not in a major way, but make some contribution and also use some information theory to get improvements and that show the connection between large language models and information theory. Okay, so to connect the two, just maybe a brief history of information theory. So back in 1948, Claude Shannon published a Bell Labs technical memorandum. It's called a mathematical theory of communication that ended up really changing the world. Okay, and in this article, he introduced the concept of entropy, which is a measure of a distribution randomness. It's denoted by h of p, and it has a very simple formula, summation of pi log of 1 over pi. And he used it for a couple of applications, one for compression, to find the minimum number of bits that you need to represent random outcomes. And the other one was communication, where you're interested in the maximum number of bits that you can convey over a random media or what we call a channel. And soon thereafter, right after 1948, people used this measure to evaluate and also to improve numerous tasks. Okay, and so um, and so he uh, so this was 948, so maybe 8 years later, um, uh, Claude Shannon published a small article. It's called "The Bandwagon," and where he says he is talking about all the applications that information theory is being used for, and he said, "Oh, like maybe we should just take a step back and not just say that it solves all the problems, but maybe just look at them a little more deeply. And just in case, here's the article we mentions these things. It may be worth article to read. This is the whole article. Okay. But sure enough, now, so this was 1948 to 956. Now it's 2026, so maybe 70 years later. And here's information theory, but in fact, there's a new bandwagon. It's called the AI bandwagon. And as I said, what I'd like to do is maybe just show some relationships between these two and maybe see how we can contribute. So much of all the progress that people have made in AI, and of course, it's a lot of progress and many contributions. A lot of it is based on just training a language model. Okay, and the training consists of one main part called pre-training, where you predict the next word, and so there are many such models, and so for example, the closed models like ChatGPT, like Gemini, those are models that that are proprietary. We don't know exactly what they are, but as you can see, they have like trillions of parameters. Let's find cursor here. They have trillions of parameters, and there are some open source models that have only hundreds of billions of parameters, but still pretty big. And they are trained on very large corpora, like corpora that contains roughly 300 trillion bytes, and so on. Okay, and you can also use like some corpora for specific applications. Like, for example, if you want to train for math, maybe you train on Stack Overflow or an archive and so on. And for some reason, I'm not seeing my cursor. Hopefully that'll be okay. All right, okay. So, but these are pretty expensive to train. So for example, a couple of years ago, Forbes published an article about the cost of training an AI model, and they estimated the cost of training them. And this is in millions of dollars. For Gemini, they estimated it at $170 million. Why am I not seeing my cursor? Okay, but in any case, you can see here. Just 1 second. Okay, so if you have a suggestion as to what I can do so you can see my cursor, let me know. But otherwise, hopefully we can do it even without it. Okay, so so training Gemini is close to $200 million. And this is actually doesn't even include salaries, just the training itself. And so it's pretty costly. And then if you want to then do some fine tuning, which is train it for specific purposes, then you can, like, for example, if you want to train for conversation or for coding or writing code or for math, so it answers questions, then what you do is what's called fine tuning, and that by itself could cost between like $500,000 to $1 million if you do it for like the way these companies like to do stuff. So that's pretty expensive still, and what we would like to do is show you that actually you can make a contribution without all these expenses, but actually it's enough to use like your Mac, and you can make like a decent, but although not great, but some decent, even though modest contributions. Okay, so and the way we're going to do it is by using existing models and then modify and add few parameters and combine models and see that we can improve state of the art on some important benchmark. Okay. And what helps us, address this really complex, billions or trillions of parameters and billions of bytes of data and so on. What helps us address it is this issue like address these really complex systems with, modest resources is that there's a sliver of silver lining, and that despite the complexity and the cost of training this system, there's an overarching and underlying simple principle that underlies them. Okay. And I think we all know that, but just in case, let's do a quick poll. So you can write in the chat. I guess this will be, okay, just a second. Did I regain? Okay. Okay. I will not be able to see because I cannot use the cursor. So you can see my cursor now, is that correct? Or not? Can you see my cursor or you cannot? You can hear me, right?
I'm not able to see along.
Okay,
So
sure.
I searched on, I mean, of course, AI, and this is the
Okay, yeah.
information. I put something on the chat. It says,
Yeah, exactly the issue is that I cannot reach the chat to open it because I
oh,
can see.
okay.
Let
It
me
says
just
you have to use the annotation tool. You have to say annotate and then spotlight. That's what it says.
annotate and then spotlight. Okay. Um, so
During
let
screen
me,
share, select annotate and then spotlight. That's what you're supposed to do,
okay,
it says. And now
I
we can
see.
see your cursor for some reason.
Yeah, so the other yeah, but because I'm not I'm using
Oh,
like yeah, you can see my screen. Because first of all, now I should be able to see see annotate and spotlight and it says seen. And let's see if it gives me some. So one participant share at a time. Advanced sharing option. Share now. We can start also now. The issue is let's see what happens if I just do this. So now we have the same issue. Yeah.
yeah, your cursor disappears when you go full screen.
Yes. Right. Yeah. Okay.
Maybe you should unshare and share again. Maybe while you're sharing, you'll get an option.
Okay. And then see here. So these are the same options that we saw before. And see here. Okay, so let's do this. I don't know if you could see the answers before, but so let's just do this because at this point I can still see. So how many, just how many of you have used ChatGPT? You can raise your hand because I can see you. Perfect. And how many of you know what GPT stands for? Okay, so some of you, right? Very good. So it stands for, it's written here, it stands for Generative Pre-trained Transformer. And what this means is transformer is just a way of predicting.
Your slides.
Second?
You can't see your slides.
Oh, I can see the slides. All right. Okay, then we're back. Let's go back to the, yeah, no worries. Okay. So share. Let me try one more thing. Let's do this. And now, how about now? Can you see the cursor?
Yeah, yeah. You can see both the
Okay.
slides. Uh,
Okay. So no, but it disappeared again. All right. Okay, no worries. Okay, so it stands for generative pre-trained transformer. Transformer is just a neural network that predicts the next word, and pre-trained means you're pre-training on on a lot of data, as we said. And generative means that you use it to predict like the next word. You can generate the next word. So basically what it says is that this whole very complicated system is based on a very simple idea of a language model. So all language models, they're stochastic, they're sequential, and a pre-trained, namely they use vast amount of data to estimate the conditional probabilities of words given contexts. So namely for all words, they find an estimate for the probability of.
Alone, just to interrupt, I'm sorry to interrupt. I'm not sure if the people in the room are able to see it, but I just see a blank white screen.
Yeah, we are not able to see the content either.
Okay,
Yeah.
so sure. Okay, no. So we'll just we know how. So I was hoping that doing it differently from the way I did it before would help, but it didn't. So let's just go desktop one, and I'll just share the desktop, which is what I did in the first place. Okay, cool. And so now I think you will be able to see. Hopefully, is that correct? Now you can see.
Yes, it
Yeah.
works.
Okay,
Yes.
cool. Okay. Yeah. Okay. Cool. So we still have this issue with the cursor. I think it should be fine. Okay. So for all words in the dictionary, they find a probability that any word like the word I or you will appear first, and a probability that of a second word given the first one, and so on. And then using the chain of probability, once they find this huge dictionary of estimates, probability of any word given any context, so to speak. Then you can use the chain of probability to find the probability of any sequence of words, which is going to be the product of these words. And if we abbreviate by W superscript I, the sequence of words W1 up to WI, then we can write it as the probability of a sequence of length NQWN is the product of the probability of WI given the previous I minus 1 words. Okay. And when they train it, they're trying to optimize something. And that gives them a way to evaluate the performance. And the nice thing is they always evaluate it in just one single way, which is called perplexity. Okay? So as we said, the probability that they assign to a sequence of words is just the product of the conditional probabilities. And basically it's a product of n estimates for each word given the previous words. And the perplexity is just defined as 1 over this probability of a sequence to the power of 1 over n. So basically what it is you take this product of n conditional probabilities and take the nth root of that. And when you do that, clearly what you get is just a geometric average of all the conditional probabilities. So you have all these conditional probabilities, you take the geometric average of all of them for I going from 1 up to n. Okay. And so what does it mean? So for example, just to give a small interpretation. So for example, if you've seen Abraham and you are estimating a probability of Lincoln, for example, if you estimate is that it's 1 over 8, then essentially what you're saying is that Lincoln is one of 8 words that are likely to find Abraham. Of course, there could be many more, but because he gave it probability 1 over 8, he said that it's roughly 1 of 8 roughly equally likely words to appear. Okay. And so, that Lincoln is one of 8 roughly equally 8 words that are likely to follow Abraham. Okay, and so this perplexity, which is the geometric average, is just the average of number of predicted words given that follow a context. Okay, and it's good if the perplexity is small. So if the perplexity is smaller, that means that for every context, you have a few words that you think will follow it. So it goes, so the smaller the perplexity, the better the language model, and the happier you are. And if the perplexity is 1, that means that you have perfect prediction. So that means that you could actually predict every word with probability 1. So hopefully it's clear what the perplexity is. So you evaluate it on like a large data set, and you can see if your perplexity is small, then you're doing a good prediction. If it's large, then not as good. Okay, and this is also evaluated on a bunch of benchmarks. So there are quite a few of them. I'll mention just the more popular ones. So TreeBank 2 starting in 1995. It was done by the Penn Tree Bank Project as 1,000,000 words. And they come from the Wall Street Journal, and they're tagged with parts of speech. There's another benchmark called 1 billion words, starts 2013, and has 1 billion words. And these are news articles, but the sentences are shuffled, so that makes it a little less convenient, at least less useful for us because we're trying to get long contexts. And perhaps the most popular one that's being used to evaluate the perplexity or performance of language models is Wikitext 103, starts 2017 by Salesforce, contains 103 million words, and contains Wikipedia articles and therefore have also long contexts. Okay, so this is perhaps the most studied modern data set, and that's the one that we will use. Just a second here. I can move it. Okay. And so 103 million consists of training set of 102.6 and validation set of 200,000 and test set of another 200,000. Okay. And there's also a leaderboard that has been maintained. Was intended by a website called Papers with Code. And they show the text perplexity. Oh, you can see now, right? My cursor. Is that correct?
Yeah.
Yes, we can see.
Okay, yeah. Okay, good. Excellent. Okay, I'm not sure what happened. Okay, perfect. So it evaluates the perplexity, the test perplexity. So remember, you have this 200,000 words that are being kept for the test. It evaluates the perplexity on that. And it starts from 2017 and goes till 2024. And the green points here are models that with lowest test perplexities. So those are models that actually improved, lowered the perplexity, and there are 12 of those. So 1, 2 in this whatever 7 years. So 1, 2, 3, there are 12 improvements, and then there are also 12 in here, and there are also other contributions that did not improve the perplexity. These are all the gray points that you see here, all above the green line. Okay, so over 40 of those. And these are interesting not just for Wikitext, but in fact, if you look at the improvements, then you'll see that the improvement, whenever you see an improvement, it was like an improvement it was an AI milestone. It just shows you the significance of this, that if you get an improvement, like if you have an improvement in neural nets, then that also translates into an improvement here. So these things are highly correlated. So for example, neural nets, the first neural nets reduced the perplexity from a much higher perplexity than they had before, although it's not shown here. And then these are like when you start to have like deep neural nets, like 4 layers, you get an improvement here, and long short-term memory. And this one here reduced by the perplexity by 3.8. Transformers reduced the perplexity from 29.2 to 18, so by 10.5. And then after transformer, so these improvements reduced perplexity by large numbers, but after performance, which was roughly 2000, so transformers were in 2017, and it took them a few months to apply it here to Wikitext. But so since then, the improvements were smaller. So you can see like a minus 0.4 to 18.3, minus 1.3, and so on, until the last one that is listed there, which is 13.3 perplexity, in maybe early or towards the end of 23, beginning of 24. Okay, and when you look at it, then between 18, so now I should be able to even move this. Okay, yeah, maybe. Okay. Okay, so between 18 and 24, so basically 6 years, there are 6 improvements. They went down from 18.7 here to 13.3. So what is it like 5.4, 6 improvements. So roughly 0.9 perplexity reduction per improvement. So that's where we are, and that's also the data set that we worked on that I'm going to describe. Okay. And I should mention that these models do not use extra training data, so they just use Wikitext. There are other models that use external data. Like, for example, you can take ChatGPT and so on, but then obviously they use much, much more data, and we don't even know they may be using like some quotes from Wikitext, or maybe use Wikitext in other languages, and they achieve better results. But the default benchmark that people use is exactly what we show here, which is just trained on Wikitext. Okay, so here are some significant Wikitext models that were done in the last few years. So adaptive inputs. So each one has some improvements. Not sure if we should go over them. That would give 18.66, and I lost the cursor again. But if I try to, I think. Interesting. Like I keep thinking that it's in some area that of my screen that I don't expect. That's I don't. Okay, so yeah, so and then so this adaptive inputs and k-nearest neighbors is where you look at the contexts and you look at the contexts that are closest to your current context, and you see which words they followed. So that's k-nearest neighbors. Now the way it's done is they only do it for a small number of words, so you'll have infinite perplexity because you cannot predict unlikely words, but typically it's combined with other techniques to lower the perplexity. And then short format has variable length sequences and achieved 18.15, and moving average equipped gated attention mega achieved 18.07, and that's from 2023. And we'll use this in our system as well. Okay, so next I want to just relate it to information theory. So again, bring it back to information theory. So we see that that large language models work on predicting the next word, and that's something that Shannon actually looked at. That's the same mathematical theory of communication. So if you look at it, section 3, then he's looking at generating words using like Markov models, which is essentially predicting next word given a context. So he starts with, so he's using a slightly different terminology than what we use today, and also maybe a little hard to read. So I just rewrote them. So first one is looking at IID letters, where each word is each letter is probably 1/26, and you can see when you generate them, you get something that makes no sense. Every letter is equally likely. Then he looks at ID letters, but with the right frequencies. So T, for example, will have a high probability, E, and so on, and then get something that looks a little more English. Then first order Markov for letters, and you can see that it looks, again, you're closer to English. Then second order on the Markov, and then you can see here things more English-like. And then he moves from letters to words. So these are independent words with the right probabilities. So you get this, like representing and speedily is as good APT, or come can different. So these are independent words, but the word makes sense, right? And then if you just look the next thing, which is this first order Markov words. So you get this, just every word just depends on the previous word, and see that they had an in frontal attack on English writer, that the character of this point is therefore another method for the letters that. So that already looks, I would say, fairly close to English. And actually, when you see that just like first order Markov gives you something which is so English-like, it makes it a little less surprising that when you add 70 years of technology from 1948 to maybe 2018, or Transformers came by. So if you add 70 years of technology and billions of dollars in training, then you'll be able to produce English. If just like first order gives you some hope that maybe it's not an impossible task. Okay, cool. So the first thing I want to do is relate perplexity to cross entropy. And for simplicity, I'll show it for IID distribution. So entropy we know is summation P log 1 over P, and we'll see what cross entropy is in a second. So related quantity. So as we said before, perplexity was the geometric average of the conditional probabilities. So it's the product of the conditional probabilities and the nth root of that. So if we take log of a perplexity, namely log of this, then what we get, so 1 over n comes outside, so it's 1 over n log of the product, and log of the product is sum of the logs. So it's 1 over n summation of log of 1 over q on the conditional probability. Okay, now we're doing it here. It will be almost the same if we do it for distribution memory, but we're doing it for IID distributions. And so if it's IID distribution, then q, the conditional probability is just q of I. So it's 1 over n summation log of 1 over the probability of each word. And then what we can do is we can define NW to be the number of times that word W appears. So for example, if we have the sentence no is no, then then is appeared just once and no appeared twice. Okay, and using this notation, we can write this summation. So each word W will appear NW times. So it's NW times log of 1 over Q of W, and then we put the N inside. So it's summation of NW over N times log of 1 over QW. And I'm still going to try and resurrect my cursor here, which I'm not sure why. Cannot. Sorry. Okay. Okay. And now by the weak law of large numbers, as n increases, then the number of times that the word W appeared n on W is going to be, when normalized by n, the fraction of times will appear will be just the probability. So this will become just summation of the probability of W times log of 1 over QW. And this is what we define as the cross entropy. So, so the entropy is summation of P log 1 over P. And that has the interpretation that the number of number of bits that you use to encode W is log of 1 over the probability. And so it's the expected number. And this is just the expected number where instead of using P, using Q. So you have an underlying distribution that has probability P, but your estimate that you came up with during pre-training is Q. So what you see is that log of the perplexity is just this cross entropy summation of P log 1 over Q. Okay, and what that means is that actually entropy, so there's one difference, which is entropy uses log. So if you take log of the perplexity, then log of the perplexity is kind of the limit of how well you can learn. So if you learn, if Q is equal to W, log of the perplexity is going to give you just the entropy. But if what you learn is Q, which is not exactly W, you get this cross entropy, the entropy of when the underlying distribution is P, but your estimate was Q. And this HPQ is always going to be bigger than H of P because, as we know, the entropy is the fewest number of bits that you need, and it's when Q is equal to P. Are we good, or do we have any questions? Okay, cool. Okay, so that's what we need. Okay, and okay, so so that brings us to this concept of compressing or estimating distributions when distribution is not known has existed in information theory. It's called universal compression. So you're trying to compress a source, but you don't know the distribution. And essentially, it's the same as the problem of learning the distribution. And so let P be an IID distribution over K symbols with entropy H of P. So the entropy, because P is over K symbols, the entropy is always going to be at most log of K. And typically, like in English, it's going to be much, much smaller than log of K. So this will appear in a second. So typically it's much, much smaller than log K. Okay. So we want to compress samples from P. So when P is known, if you can compress one sample to the entropy, maybe +1, which we can ignore.
Alon, sorry
Yes.
to interrupt. I think it might be worth checking if the people in the room are able to see and hear you. It feels looks like their video is sort of stalling. I don't know if you see it like that.
Okay, so I do not see, but maybe they can tell us.
Arvind, are you guys there? I
They
think,
disappeared.
yeah. So let me just call Arvind here. Can you hold on 1 minute? Sorry. I think
Yeah.
this having some issues there.
Meanwhile, I'm going to try to see if I can do something about the cursor.
So it looks like they're facing some network issues. I'm not in the room. I'm in some other place. I don't
Yeah.
seem to have any network issues, but they suddenly have gotten into some network issue. I mean, hold on for a few minutes alone. Sorry about that.
Sure.
They
Yeah.
should be
No
back.
noise. Noise. Noise.
How are you doing otherwise?
I'm doing okay. Yeah. Doing fine. Yeah.
Okay, good. Let's just pause for a little while.
Am I going good speed in you? Do you
Yeah,
think?
yeah. I think it's good. So there's one question I had real quick on the. So if you go to the perplexity, you're relating it to cross entropy and you're going to compression. I can see that direction. But the other thing that you could do, for instance, if you go to that expression, you can sort of multiply and divide by, you can multiply and divide by P of W inside the log, right? And then you get the empirical entropy plus,
absolutely.
plus KL divergence, right?
Exactly. So the cross entropy is, you're absolutely right, is the entropy plus the KL divergence. That's correct.
Yeah. So if you take a fixed context length for your say Wikitext 103 or something, the first term, the entropy term will be like a lower bound, right? No model can beat that.
Correct.
So what is that number for Wikitext 103 for? I mean, but these things are huge.
But we don't know,
isn't it?
because we don't know the issue is that we don't know the actual distribution, so we don't know what the entropy of English
No,
is.
but that's the empirical thing, right?
No.
P is the
I don't think so.
empirical.
No. The way we're doing it here, P is the underlying distribution, which we don't know.
So Q, that is Q, no? P is the NW by N.
Right. So this will converge to P, right? But we don't like if the distribution was IID, of all people, that, as you know, if the alphabet was small, then yes, we would know, right? If it was IID and small alphabet, then yes, we would be able to learn P, and then we'll be able to plug it in. But two things hurt us. One is the alphabet is very large, so we don't get that convergence. And two, the memory is also large, so we cannot evaluate this. Yeah.
Okay.
But yeah, you're absolutely right. Yeah, and this, yeah. So what we have is the entropy plus the KL divergence. The KL divergence is actually the redundancy. I'm not using those words, but everything is correct. Yes. Yeah.
Okay.
Yeah.
Let's just hope these guys come back. He's calling me again. Just hold on a minute.
Okay, sure.
Yes, Simon. Yeah. Okay. Let me ask Alon about what he wants to do also. I mean, it'll take like 5-10 minutes, is it? Is that what you think? Oh, okay. Do you guys want to come here to the ICSR building? It'll take about 5 minutes. I can set up a place for you here. How many of you are there? I mean, over. Do you want to come here? Yeah, why don't you come to the third floor in ICSR? I'll arrange a place for you. Network seems stable here. Huh? Come. Okay, so I'm asking them to shift to
Yeah,
where I am.
I heard you.
Is that okay, Alon? It'll take about 10 minutes.
Yeah. No, it's all good. Yeah, don't worry.
Sorry, I think this looks like there was some maintenance. It's just something they're doing there. They've just decided to shut it or something.
Yeah,
So
no,
they're moving here. Let me make arrangements for them here to sit in a place.
okay.
I'll be back in about 5 minutes.
Okay, sure.
Thanks a lot for being
Yeah,
understanding.
no,
I'm really sorry.
no worries.
Okay.
No
Okay.
worries.
Arun, can you hear us? Sorry for the.
Yes, I can. Yeah, I can.
Yeah, really sorry for that disruption. There was some
No.
network issue down in the EE department, and we had to relocate.
No worries.
Yeah.
Mhm.
So could you go back a little? Maybe is that okay with you? Maybe.
Yeah, I can go wherever you want. So you can see this slide. Is that correct?
Yeah,
And you
yeah.
want to
We
go
can see.
further?
Yeah.
Is further back? Okay, no worries.
Yeah.
Where
Yeah.
this
No, after this. So we were there
after
at the
this,
position where
no
we
problem.
were talking.
And
Yeah.
then I spoke about significant.
Yeah. After this, yes.
Okay. Yeah, and after this is this was the slide after that. So the previous
So
slide.
from about here, yeah, from about here to be okay.
Okay, sure. So let me just go over the slide. This is the slide just showing all of it. So basically, in 1948, the same breakthrough paper, mathematical theory of communication. Shannon also wanted to look at English and see how well we could compress English, and he said let's model it as a Markov chain. And he showed what happens when you look at word models, and then he looks at letter models, and then first order word models. And it shows that if you take just first order Markov, so after every word, you look at the right distribution of the next word. And mind you, this is 1948. So, and you get this sentence that reads, I'd say almost like English. And if you can get such a good, reproduction of English with just like first order relation, and you can imagine that, with the models that they have now with, billions of parameters, trillions, then they should be able to get something that reads like English. So we're good?
Yeah, we are good.
Okay, cool. Okay, so what we want to do now is relate perplexity to a quantity which is related to entropy. So entropy, if you remember, was summation of p log 1 over p. And that has the interpretation that log of 1 over p is the number of letters that you want, the number of bits that you want to represent as a symbol. So if something is, for example, if we have an outcome that has probability 1 over 8, you want to allocate it log 8, which is 3 bits. So it's the expected number of bits. And cross entropy is going to be a closely related property. We'll get to it from the perplexity. So, and for simplicity, we're going to show it for ID distributions, but it's a very simple extension to distributions with memory. So what we said before was that the perplexity was the product of the conditional probabilities raised to the 1 over n. Okay, that's what we said before. And so if we take the log of the perplexity, we'll get the log of this, and log of that is just 1 over n times log of the product, and log of the product is the sum of the logs, so it's 1 over n, summation of log of 1 over the conditional probabilities, okay? And then because we're assuming that these are IID distributions, then the conditional probability of WI given the previous ones, just the probability Q of WI. So it's log of Q of WI. And then we're going to let NW denote the number of times that a word W appears. So for example, if we have no is no, then N is 1 because it appeared once, and no is twice because it appeared twice. And so here in the sum, every word W will appear NW times. So this will become summation of all the words of NW times log of 1 over Q of W. And then we put N inside. And by the weak law of large numbers, NW over N, because we're assuming IID distributions, then NW over N will converge to just P of W. So it's summation of P of W log of 1 over Q of W, which is what we denote by the cross entropy of P and Q. So it's the expected number of bits that you need to encode elements generated by P when you assume that the distribution is Q. So like when they train, they assume that the distribution is Q, so they'll use log of 1 over Q bits, but it actually is generated by P. So what the log of their perplexity is going to be just this cross entropy. And this cross entropy is always bigger than at least the entropy itself, because the entropy is with the best encoding. And the difference between them, we had this discussion with Professor Tankaraj, and he was noting, which is correct, the difference between them is the KL divergence. So the cross entropy which is just log of the perplexity, is just the entropy plus the KL divergence between the entropy, between the dual distribution P and the distribution that you learn Q. Are we okay with that?
Yeah.
Okay, perfect. Okay, cool. So that is closely related to universal compression, which is what happens in information theory when you want to compress data and you don't know the underlying distribution. So if you knew the distribution, you need the entropy H of P. If you don't know the distribution, then you need to essentially learn it and you'll incur some loss. So again, we're going to assume that we have an IID distribution to begin with. So IID distribution of a K symbol distribution is P. Then its entropy is H of P is at most log of K. And in reality, it typically is much, much less than log K. For example, if we look at English, then if you remember, then we said that English has, like, let's say, Wikitext has 270,000 words. So log of that is a large number. But as we said, the perplexity they're getting is roughly 13, and log of that is much smaller. So typically, the entropy is much smaller than log of the number of symbols. And so if you want to compress samples from this distribution P, so if P is known, then even if you have a single sample, then you get the entropy, maybe +1 for round off. And if you have n samples, then you need n times H of P, maybe +1. Okay. If the distribution is unknown, this is what universal compression tells you. Then if you have one sample, then you need log of K because you don't know anything. So you just need log of the alphabet size. But if you have n samples, then you need n times H of P, which is the entropy, plus a term that's called the redundancy, which is K minus 1, alphabet minus 1, over 2 times log n. Okay, so you need this term, which is n times the entropy, grows linearly in n, plus a term that grows logarithmically in n. And this is your loss for not knowing the distribution. And so this redundancy is the extra number of bits beyond the entropy, beyond the number of bits when P is known. So for all n samples, as we saw here, you need K minus 1 over 2 times log n. This is your penalty for not knowing the distribution. And if you're doing it per sample, you divide by n, you'll get K minus 1 over 2 log n over n. This will go as your sequence length increases, will go to 0. So that means that you can compress as if you know the distribution. Are we good?
Yeah.
Perfect. Okay. Now, so this is good news. And then if you have sources with memory, then you can just extend the ID results. So if you can look at sources, you can learn distribution, follow each state. So you see the state, you learn the distribution after that. And so if you have S states, and each one eventually you'll be able to learn. So you'll have this redundancy 0 for each. And anything S states times 0 is also 0. So as n goes to infinity, the redundancy, even for any Markov chain, any order, is going to go to 0. Because each state you learn well, and you multiply 0 by S, you'll still get 0. Okay, so that's good. And for that, you can extend it to stationary Grotic processes, and you can also compress those with redundancy that goes to 0. So in all those cases, you can compress if you know P in advance. That's kind of like the IT miracle. That you can learn without knowing the distribution in advance. However, there's some sad news, which is that all this holds as n goes to infinity. Okay, and asymptotically, and in life, if we typically don't live in the asymptotic regime, and specifically when we're talking about English, we're talking about large alphabet. So English, the vocabulary is large. For Wikitext 103, it's 270,000 words. So if we look at K minus 1 over 2 log n over n, then k is 270,000. So that does not go to infinity. And you might argue that, okay, but n is very large because, we look at trillions of words. But in fact, the n that you care about, because we have distributions memory, is the number of times the context appears, because you learn per context. So n, the effective n, is how many times the context appears. And you're looking at long context, so each one appears very few times. Like if you look at a context of, let's say, 10 words, how many times does this context appear? Even if you Google, it's going to be a small number of times. So n is not large, actually, okay? And the redundancy is actually quite large if you calculate it that way. Now, there are ways to partially address this, and both I and Professor Tangaraj have worked on things like that, but more work needs to be needed, to get these results. But there are ways to address this issue. Basically, you modify your definition of redundancy in a way that still makes sense, but is a little more amenable for large alphabets. Okay, so what LLM does, so the problem is essentially the same, right? It's like they're looking perplexity. If you look at the log, that's the cross entropy, and that's the entropy plus the redundancy. Information theory, if your alphabet is small, that shows you can learn. If it's not small, then some work, but more work needs to be done. And that's what they're doing, and they're taking a different approach. So their approach, next word, estimation, started possibly with Bengio et al. In 2003 and got a big boost from an algorithm called Word2Vec by Mikolov et al. 10 years later. And in this approach, the words are mapped into vectors, typically like 1,024 dimensions. Okay, so what you want to do is you want to learn two mappings. You want to map words, word W, to a vector EW, that the representation of this word, and some embedding. Your alphabet in this case is fixed, so you can just have a table that says this is what I learned. And then you want to also map context C to a vector EC, and this has to be done with the function because your context is going to keep changing and so on. Okay, so given a context C, then so you have a context C, like this is maybe you passed 100 words or 256 words, something like that. So given a context C, then for every word W, what you do is you take the inner product of the embedding of the context and the embedding of the word, call it RW. And this you can view it as the unnormalized log probability, and you can also call it logit. And then to find the probability of each word, you do what's called softmax. So the probability that you assign to a W is, because this is viewed as the log probability, so it's the exponent of this inner product, and then you just normalize it by the sum of all words, so that your probability for every word is going to, the value given to every word is going to be probability. They sum to 1. So it's called softmax, and then if you let our vector be the collection of all logits of all the words, and Q be the collection of all the probabilities of all the words, then you can just write it in shorthand that the vector Q is the softmax of the vector of the logits. Okay, cool. So we're going to so this is what's done, and this is basically some variations of this achieve the benchmarks, different benchmark performances that we saw. And so we're going to look at two ways of adapting things. And one is to improve the estimator, and the other one is to take ensemble of estimators. Okay, so let's start with the first one, improving. You fine-tune. We're going to fine-tune our estimator. So we're going to do it by turning up the heat. In some applications, so one application is generative AI, but there are other applications people look at, like so text generation, calibration, and what they do is they post-tune the models, and the inner product, remember, was the embedding of the context times the inner product with the embedding of the word, how they're related. Okay. And this, as we said, was the unnormalized log probability, or the logit. So what you could do is you can take take this product and divide it or normalize it by a temperature parameter tau. So instead of RW, you're looking at RW over tau. So the probability that you'll assign is going to used to be the softmax, the exponential of RW divided by the sum. Now it's going to be the exponent of RW over tau divided again by the same sum. Okay, and then Q, the distribution was the softmax of the logits. Now it's the softmax of the logit vector divided by tau. Same thing. And so it's basically a softmax in a linear function of RW. Okay, and so to see why it's called temperature, so you can see that the probability that you assign is proportional to an exponent in RT. It's proportional to this exponent in RW over tau. Okay, and so and we can see what happens to how flat this mapping is. So if tau, the temperature increases, then we take RW divided by tau and make it more flat, right? So this will become more flat, okay? And that means that when you generate the text, so this terminology comes from text generation. So when you generate the text, then all the words will get roughly the same probability, so that it becomes more random, as opposed to a very skewed, like some words are very likely and so on. This is everything divided by a large tau. And so now every word is the same probability, so it becomes more random. So it's like you raise the temperature. And conversely, if tau decreases, then some values will be very high, some values will be very low. So this will be more sharp. And therefore some words will be more likely and other words will be less likely. So the randomness will decrease. So that's what, so the temperature thing goes down. So that's why it's called the temperature parameter. Okay. Now, this is why they call it, but what we need here is actually not this interpretation of randomness, but rather the fact that this division by tau allow us to control the flatness of the mapping. So it gives us a little more control to not say that we're not looking at a specific exponent, but a collection of exponents, and we can try to optimize. Okay, so this part explains the temperature, but this is what we need. Okay, so as we said, the probability is exponent of e to the RW. And then, as we said, you can ask why unitary exponent. So you can find the best exponent with the best temperature. Okay. And then this is what we described in the previous slide. And then you can say why use the same exponent for both likely and unlikely words. Maybe the mapping should be different for words that are more likely. The inner product is very high. Maybe you don't want, you want a different mapping, different exponent at that point than in other regions. So you can divide it into k intervals, and for each interval, then you have a different exponent, and you can multiply by a constant. You do that so that the mapping will be continuous, because it doesn't make sense that there'll be like jumps. So you just use beta i's to make it continuous. Okay, and then you can look at the results. So remember, adaptive inputs was one of the estimators that we mentioned, and it's with exponent 1, the perplexity was 18.66. If you normalize by tau and optimize for tau, then it's essentially the same. And if you look at the piecewise exponents that we described here, then it goes to 18.44. And for mega, you get an improvement even with just a single temperature, and further improvement for piecewise, and for short former, again, some improvement. Okay, so you get some improvement this way. And I should mention that for pre-training, using a different interpretation, something similar was done by Ganea et al. In 2019. Okay, so this is improving a single estimator. Now we can talk about ensemble of estimators. So let's talk about, not the worldwide WQ, but W4. Let's talk about what we're talking about ensembles. what are ensembles, why we use them, where do we use them, and which ensembles we should use. So what are some ensembles? Ensembles are just combination of estimators, and they're used to improve results. And this, in our case, is to reduce perplexity. Why do people use ensembles? Because they want to exploit, like you have maybe different estimators, and maybe one estimator works well for verbs, and another ones for adjectives, and so on. So you want to exploit the advantages of each one, and you also want to add diversity of different estimators. And in general, when you add more estimates, you reduce the randomness. So each one has some randomness, and when you take a bunch of them, take some average, the randomness goes down, and you get the signal, and you reduce the noise. So that's why they use them. And where is it used? It's used in many, many applications, including LLMs. And if in fact, I didn't mention it, but if you looked at the leaderboard that we had, then the lowest perplexity that's achieved there is achieved by an ensemble of estimate. I think it was called ensemble of all or something like that. Now, what are we going to look at? We're going to look at linear estimators, which are the basic estimators that people use, and also was used by the lowest perplexity estimator there. And in this case, we're trying to find weights, the weights that we give each estimator, and we'll look at static weights and adaptive weights, and we'll explain why we're looking at adaptive weights, and then we'll look at nonlinear ensembles. Okay, and at least in this context, people have not looked at this. Okay, right. So first, linear ensembles. So suppose you have a distribution, two distribution, Q1, let's say this is the distribution over the words, you have just 3 words, and Q2, maybe this is the distribution, and you want to assign weights alpha 1 to Q1 and alpha 2 to Q2, and alpha 2, they have to sum to 1, so alpha 2 is 1 minus alpha 1. And your sample is going to be Q, which is just alpha 1 Q1 plus alpha 2 Q2, like Q1 and Q2 estimators, alpha 1, alpha 2 sum to 1. So Q is also this convex combination. Q is also a distribution, also an estimator. Okay. And so what you want to do is you want to find alpha 1 and therefore alpha 2 that will minimize the validation perplexity of Q. So there's a validation. So remember, there's a training that you have trained the model on, and what we're doing is post-training. So you take the validation set and you find the alpha that will give you the best combination of the 2 estimators. Okay. And then what you do is you'll find this alpha that will give you this Q, and you report the performance Q on the test perplexity on the 200,000 remaining words. Okay, so if you look at KNN plus ADT, then with transform logic means like the piecewise exponents that we discussed, the perplexity. So for ADT with the transform, just ADT by itself, this improved. So if you take ADT and improve it the way we discussed with the piecewise exponents, the perplexity is 18.45. And if you just use these weights, we're calling them static because these are just fixed weights, then it goes from 18.5 to 15.82. So it's a fairly large improvement. Okay. This is still larger than the best that we saw. The best that we saw was something like 13.3. Okay. And then the question is, so this is just like fixed static weights, like you give ADT, let's say 75.75 weight, and KNN 1/4. Okay. And the next question to ask is whether you can get something from nothing. What do we mean by that? So suppose I told you that this is one distribution, 0.2, 0.3, 0.4, 0.3, 0.1, and this is another distribution. And we want to assign weights alpha 1 and alpha 2. They have to sum to 1, such that the ensemble is going to be alpha, this weighted average. Okay. And then so the way we said we'll choose the alpha 1 and alpha 2 before is we look at the ensemble perplexity on the validation, and we try to find a combination that minimizes the perplexity on the ensemble. So then you can definitely do that. But suppose you want to do it without calculating the ensemble perplexity, you want to find the weights without this, and also without any additional information. I just tell you, this is my first estimator, give me this distribution on the words. This is my second estimator, give me this distribution of words. And I want to find which weights I should use. So which alpha, what should alpha 1 and alpha 2 be? What do you think?
if you know how bad the estimators Q1 and Q2 are, you could choose the interpolation weights based on that. So if you know like the KL between your Q1 and like the actually, yeah, maybe something like
Yeah, you're right. You're
Yeah.
right. But here we want to do it without any additional. So we don't know the performance. I just tell you these are the two, my two estimates. You're right.
Some kind of inverse variance sort of a thing.
The what?
Some kind of inverse variance kind of a thing.
Okay, yeah. So that's the direction that we're going. But this question is a little hard, so I'll make it a little easier. Say we just want to know which one is larger. Like, should this one be given bigger weight? Yeah, you're going in the right direction. We're just making it a little easier. Let's say we just want to find which one should have like a higher weight. Okay, so we've been going for a long time, so I'm going to give you a hint. Okay, and if it's not big enough of hint, this is a big hint. And if that's not big enough, let's, in the interest of time, this is a whatever 13 hint. And at this point, we should be able to guess what's going on. So this H and Shannon talking about entropy. So so you can look at the entropy of these two distributions, okay? And a natural question is, so I think someone mentioned like the variance. That could probably be another approach. You need to define it, right? It's the variance of, these are probabilities, right? So, but something along these lines might work. So first, why should entropy help, and then how it should help? Okay. So in other words, I give you the entropy of Q1, and I give you the entropy of Q2. These two distributions, and the question is, which one would you trust more? So we have these two questions: why do we use it, and how do we use it? And as we'll see, we'll have one solution, or if you want to, if you want to say one stone that will kill these two problems or two birds. And I'm imagining that some of you there might be vegetarian. So as you see, then we're not killing the birds, we're just scaring them away. So it's okay. Right. Okay. So all right. So this is what we want to do. And to see, so let's look at a tool that will help us see what we should do. And this is clearly an information theoretic concept that one could use. Okay, right. So let's just remind ourselves of the maximum entropy principle. It was derived by Jane in like 60 years ago, almost 70 years ago. And it said that of all distributions of a given state, so you have look at a collection of distributions, and that satisfy certain constraint. I'll give you some examples. So you have a bunch of distribution, and this satisfies certain, like your observation, like maybe the average is something. So if all distributions satisfy a given constraint, the most representative is the one with the highest entropy. So this is the maximum entropy principle. Okay, and so in other ways, another way to say it is that you should look at the explanation that's consistent with the observation and yet is the least committal. So if you have a high entropy, that means you're making the least commitment about the value. You're not saying it's always going to be the value, the letter A. You just say you're going to be, uniform, not committing, or the one that is least prone to overfitting. So you're not overfitting your data. So that's what this principle says. Okay, so let's do a couple of examples of max ent. So I'm putting game theory because this is a die theory. It's just like rolling a die. So if I'm going to roll a die, 1 up to 6, okay, domain is 1 up to 6, and let's say I'm not giving you any information, then what are we going to assume about the distribution? It makes sense. We'll assume it's uniform between 1 up to 6. That's the highest maximum entropy distribution. Or in physics, I'm just giving a few areas where this maximum entropy principle is used. So look at physics, and we have molecules, and maybe each molecule is in space between -1 and +1, and maybe 3-dimensional space. Okay, and again, we're not giving any information. So what distribution we'll assume? We assume that each one is uniform. Each molecule is distributed uniformly between -1 and 1, and they're independent of each other. And that will maximize the entropy. So this is typically what you do, and it satisfies the max ent. Now let's look at some constraints. Operations research, you have a queue, and you're interested in the service time. Service time is a real number between a positive real number. Okay, now you observe that the mean service time, you observe the queue maybe 100 times, you see that the mean is 10, and you ask yourself, which distribution would you assume? So what the distribution these people assume? They assume exponential distribution, right? With mean mu, and indeed, if you look at distribution maximize the entropy under this constraint that the mean is mu, that is also the exponential. So this is again max entropy. Or if you look at communications, like many of us, and you have a noise, and let's say the noise, let's say it's just one dimensional, the noise is a real number between minus infinity and infinity, and let's say it has mean mu and variance sigma square. What are we going to assume about the noise? We're going to assume that it's normal with mean mu and variance sigma square. And again, this maximizes the entropy under these constraints. So this principle is, used pretty widely, okay? And you can think of a couple of motivations. First, like second law of the thermodynamics says the entropy increases over time. So what you'll observe will tend to have large entropy. And another one is another motivation for this is the asymptotic equipotation property. For those of you who know information theory, it says that if you look at the distribution, the volume is roughly 2 to the entropy. So if it has a larger volume, it's more likely to happen. So that's another reason for that. Okay. So how are we going to use this for our problem? So we want to use entropy as an ensemble parameter. So we have two distributions. So we have two estimators. The estimator actually are given to us. So we know the exact distribution, we know the exact probability that it gives to each word. We can calculate the entropy. And given the entropies, we want to find the weights. So alpha 1 of each, these two entropies. Okay, I'll just abbreviate it still by alpha 1, but it's a function now of these two entropies. And then alpha 2, which is just the complement, 1 minus alpha 1. And we want to find the alpha 1 and alpha 2, these functions, such as when we take this function, this ensemble Q, which is alpha 1 Q1 plus alpha 2 Q2. But now, again, this alpha 1 and alpha 2 are dependent on the entropy that minimizes the perplexity over the validation data. And for that, we use the feed-forward network and to find this alpha 1, alpha 2, and then we use to find over the validation, we find the alpha 1, alpha 2, and then we evaluate it over the test set. Okay, is that clear? And what we expect and what do we expect to alpha 1? How would you expect alpha 1, alpha 2 to behave? So if the entropy of Q1 increases, we expect the weight that we give to alpha 1 to maybe increase, and the entropy of Q2 is high, that maybe expect by max entropy, we expect to give more credence to this estimator, so alpha 2 to increase. Okay, so let's look at the results. So let's look at entropy, this exact question, entropy versus weight. So we'll look at combining ADT and KNN. This is like the typical combination that people use. So this is, here we're showing on the horizontal axis the KNN entropy, and on the vertical axis the ADT entropy. And here we show the weight that we're going to give ADT, and the weight is color-coded. So blue means that we give, in this region, we give ADT low weight, and we give, therefore, KNN high weight. And over here, it's yellow. That means we give ADT high weight and KNN low weight. So let's see what happens. So ADT, if the entropy, as the entropy of ADT increases, that means so we're moving in this direction on the y-axis, okay? Then we see that the weight decreases, right? Because this is the color is the ADT weight, which becomes blue, which is small. So as the entropy increases, the weight of ADT of adaptive inputs increases. And if we look at KNN, as the entropy of KNN increases, that means we're moving in this direction. Then what we can see is that the weight of ADT, which is what is shown here, the weight of ADT becomes yellow, increases, and therefore the weight of KNN decreases. So we see that higher entropy implies lower weight, And this is the opposite of what we expected, right? Because by max entropy, we thought, oh, we should go for the higher entropy distributions. So if something has a high entropy, we should give it a high weight. But in fact, these are the experiments. These results, the results of the experiments show that it's the opposite. So the question is, did we just contradict max ent? And the answer is no. In fact, what we show agrees with it because it's a different setup. So max ent says that you should, if you get observations, you should choose an estimate that's consistent but has the highest entropy. So you should choose a consistent estimate that has the highest entropy. That's max ent. But that's not what we have here, because what we have here is two estimators. We're given two estimators. These estimators are pretty good, right? I mean, like each of them has achieved like pretty good results in its time. So they're pretty good, and they presumably use something that's equivalent to max ent already. So they provided the estimates. So when you look at the estimate with the lower entropy, presumably it used max ent, and it showed it, and what it shows is that the highest consistent. So it's trying to give is trying to find. So it sees the observation, right? It tries to give you an estimate with high entropy, but the highest entropy that it can find that's consistent with the data is lower than the other estimator. So that means that it must be more confident, because if it was not confident, that would give estimate that has a high entropy. But the reason it gives you something which is lower entropy is because it found some constraints there that force it to give a lower distribution, lower entropy, so it's more confident about what it's doing. Okay, and therefore, because it's more confident, we should give it high weight. Because if it made no observations, it would just assume it's uniform, give very, very high entropy, and that's because it doesn't see it doesn't learn anything. But if it could learn something, then it's able to reduce the entropy, even though it's trying to give the highest that it can. But it learned a lot, so it reduces the entropy. So we see that lower entropy estimator is more confident, and therefore should give it higher weight, and that's really what's happening. Okay. Now, this is not the only explanation. There are other explanations that you could use, related explanations. One is Occam's razor that says that shorter explanations are best. So you can think of maybe low entropy as shorter explanations, minimum description length, shortest model and outcome description. You can think of universal compression. Why did I repeat? I'm not sure, but universal compression, what I wanted to say, I apologize for this, is that when you start to learn, like for example, there's estimated called like EDHAF, when you try to learn the estimation, but in the beginning you assume it's uniform, and the more data you have, you get to the right distribution, which is here, which have much lower entropy than the uniform distribution. So there are two, the more data you have, the more confident you are, you reduce the entropy. Okay, so you should give low entropy estimators more weight. So I should mention that related. So there's a paper from 2021 that also used entropy, but they only used the entropy of ADT. So we're using it to define the weights that we give the different estimators, and we use the entropy of both of them. They just use the entropy of ADT to define when they need to use KNN. KNN is less efficient, so they use it just to increase efficiency. Okay, so let's see what perplexity we get with the entropy parameters. So KNN plus ADT, and again with adaptive temperature. So we take the improved ADT, that one that we improved, and with static logic weights, then we said before you get 15.82, and when you add entropy, it goes down to 15.12. So you just add, when you try to decide on the weights, you just also use entropy, and you get perplexity goes down to 15.12. Okay, now let me check the time. 12. Okay, so maybe you could also look at the distance. I'm going to so when you look at the context, you know what the context is, and you know what context you've seen in the past. And KNN, remember, is K nearest neighbors. So you can find like you can look at the how far you are in the your nearest neighbor, how close it is to the current context, and then you can use that also to find the weight. And again, there were people use this in and if you have a smaller distance, they give it higher weight. You can do that. And the people did something similar to that in a somewhat different context as well. So there are lots of work in this area. So we found that we come up with something, and it's a little difficult to find something that nobody has done something somewhat similar to that. Okay, so they got higher complexity than we did again. Okay. And so then you can look at combining the four estimators. So this is also like for the minimum distance. Let's keep that. And so you can do that, and then you get some results a little better. And then the next thing I want to talk about is whether we should use a linear estimator to begin with. So the target word is the word that follow the context. So for example, if we look at today is, and then in new, actually for mine too, right? Yeah, we just passed midnight. Yeah, oh yeah, exactly midnight. Okay, so like in 1 second is going to be Monday here too. So with this context, if this is the sentence, then this is the target word. It's the word that follows the context, okay? So what you can do is you can look at the fraction of words that were the target. What do we mean by that? You can look at a fraction of words W with a given. So you have two estimators, right? And we try to combine them. Let's say we have KNN and we have ADT. Each of them gives you a distribution over the words. And they're shown here. Here this probability from 0 to 1 that they give each word. So remember we have 200,000 training words for the validation. So we have a lot of data, and what we do is we group them in bins, and for each bin we look at the number for the words that had this given probability. Let's say 0.5, KNN give probability 0.5, and let's say ADT give probability 0.3. This is this bin. We look at all the words that are in this bin, and we see what fraction of them were actually the word that followed. Okay. And so this in some sense, this should give us roughly the probability that words with this respective probability. So it should tell us, if we look at words that KNN gives 50% and ADT gives 30% of being the next word. If you look at this combination, it tells us what fraction of them actually ended up being the actual word, the target word. Okay. And if you're using a linear ensemble to get alpha times the probability of KNN plus alpha bar times the probability of ADT, that would mean that if you drew a straight line, then you'd have some straight line that corresponds to alpha and alpha bar. This should be a constant. But the probability they happen. But as you see here, there's no straight line that will give a constant. For example, if you look at this, then clearly like here it's more yellow, which means it's not constant, but also like in the middle, it kind of like is more bluish here and becomes more yellow as it goes to the sides. Okay, so you can see there's no straight line here that will give you a constant. So that means that there's no such line. So P, the actual P that we see is not a linear combination. So then you can say, okay, let's look at nonlinear ensembles. So linear ensemble, then Q is summation of alpha I QI, and summation alpha I is 1. So this is guaranteed to be a distribution. Nonlinear Q is, you get Q which is proportional to some function of the different probability estimates. And this is not going to be in general distribution, because for every Q1 up to QM, you have to find some function. So you need to normalize overall words. So Q is going to be, you're looking at this function, and then the Q will be this function divided by the summation. The summation is of all W. So I'm abbreviating. So each one of them is a function of W. So here it's Q of W and divide by the sum of all W. This is going to be your estimate Q of W. Okay, so and then this function that you learn again by a feed-forward network. Okay. So when you do it, you can see that actually what this shows is the probability that we assign is shown on the top, and the actual probability of these bins that were the target word is the bottom. So in many areas it's reasonably accurate. Some areas like here maybe not so accurate, so there's some room for improvement. But like here 0.39, 0.4, so somewhat likely. I should also mention there are not so many words that get probability 1, right? I mean, because these you have 270,000 words, so most of them get very, very low probability. Most of them are right roughly here. Okay, so when we do so this is how we do that, and this gives us hope that maybe something will work out okay. And so when you look at the combination, so we look at nonlinear ensemble of these 4 like frequently used estimator, ADT, Mega, short former, and KNN. And I should say, well, for KNN, we use an estimator that was derived by Erel and Mikolov, and they did not provide the model, namely that one that will give us, given the context, will give us a distribution. But what they did provide is only the probability that give to the target word, and that's enough to calculate the actual perplexity, because we just need to see what happened to the target word. So we can do that, but because we don't have the estimate itself, we cannot do the nonlinear combination. So here we just do the linear combination for the right word. That's enough to find the perplexity. Okay, so for this estimator, it's a linear combination because we don't have the data. Okay, so this, when you combine, it gives us a new state-of-the-art perplexity. So the previous, if you remember, was actually where I abbreviate, I wrote 13.3, well, actually it's 13.29, and the new one is 12.39. Okay, and so if we go back to this leaderboard, if you remember that from 18 to 24, there were 6 improvements. Average reduction was this 18.7 for transformers to 13.3 over 6, which is 0.9. And what we get now is, so actually this is 0.29, we get 3.9. So the difference is the same. So it's 12.4. I'm just simplifying. The difference is 0.9, which is in line with what people got before. Okay, cool. Okay, so yeah, so I have some comments about the increased model size. If you people want, we can talk about it. But if not, I'm happy to go back. Summarize. So look at perplexity, which is a fundamental concept for training. And I like this concept because there's so many things you can do with AI, different tasks, and everyone has like its own benchmarks, its own result. But perplexity is something which is common to everything. It's the only way people train the pre-train, the big systems, the fundamental system, and then it's often used for the fine-tuning for specific applications, although there they might use something else. And it's a number, and it's related to information theory. It's used for LLM training and applications, and it's simple, and it's probabilistic information uses probabilistic information theory concepts. Okay, and what we did, I don't want to oversell the results. We got some improvement. Okay, and we got them by taking the model and doing piecewise, looking at piecewise temperature that improves something, and looking ensemble, both linear, where we used entropy and minimum distance. Entropy, I don't think people used for this application to reduce the way we're doing it, looking at the 2 weights and deciding. Minimum distance, they used it in a different way that was a little closer. And then we used also nonlinear estimators, and we reduced the perplexity from 13.3 to 12.4. Yeah, and so I'm not claiming that information theory is in front of AI, but maybe we're trying. This picture needs to be modified, humbled down. So like maybe we're trying to get information theory closer to the to AI. Yeah, so that's it. If you have any questions, happy to answer.
That question?
So I have a question. So you talked about how big the trained data needs to be throughout. So there's something strange happening here in the sense you kind of say that the empirical fraction counts in your test data by the weak law of large numbers. If your test data is kind of large enough, they will be equal to the real value, the real p-value in some sense. Of course, that's not, but that's kind of strange because your test data seems to be much smaller than the trained data. So the sort of you might have a really bad test sample, and that might affect your perplexity numbers. So really, we should be using infinitely large test samples, right? But we can't do that. So what are your thoughts on that sort of discrepancy?
Right. So yeah, what you're saying is totally correct. So if we had IID data, and in fact, with Professor Tangrach, we talked about it when you were on a break. If you had two things, if you had if your data was IID, makes it simpler, and two, if the alphabet was small, such that so that you can say, oh, the weak larger now could kick in. So you have IID, a small alphabet, large training data set. Then the law of large numbers will kick in and you'll get the right probabilities. And then the perplexity will actually be, log of the perplexity will be the entropy. Absolutely right. But none of these happens. The data is very far from IID, as we saw, and the alphabet is very large. So the law of large numbers does not kick in, and the log of the perplexity is much higher than the entropy. Okay, I don't know much, but it's higher than the entropy. So that's the issue that they face, they being like AI when they train it. And that's the issue that we face in information theory, that you'll have this gap. We don't live in this asymptotic world where n is very large and so on. And so the log of the perplexity will not be the entropy, but it will be, the entropy is a lower bound. It will always be above it, but right. And then the question is, how do you make it go fastest to the entropy? And that's the challenge. That's what effectively we're trying to solve here. And that's also what we grapple with when we talk about universal compression. But yes, what you said is correct.
Okay, thanks. I have one other high-level question. So, whatever you spoke about in this talk was about somehow modifying the pre-training procedure, right? I mean, at the end of the day, you're combining these different estimators according to some either linear model or according to some non-linear kind of predict, so that finally you try to make the perplexity as small as possible. How do these methods fare against other, for example, you have reward-based methods that people do, right? I mean, where there is feedback and you kind of keep fine-tuning the model post this pre-training procedure. So are those better at reducing perplexity even further, or how does this work? That is a high-level question.
Yeah, so the bottom line is I don't know. So people do use, companies do use reinforcement learning, like they ask you which is, like human reinforcement learning, they ask you which one is a better answer and so on. And that should help you reduce the perplexity, in theory at least. They could ask appropriate questions for perplexity. They don't ask it based on perplexity in this case, they ask higher level questions. So that should help you reduce perplexity. And if you do it right, probably they should be significantly more effective, in a sense that, like there's some things that you can predict well, and there's something that will be totally off. And they could tell you, like, if the purpose was to use this to reduce perplexity, which is not the case, right? They try to ask you, do you like this image better or this image? Like these images that I show, I used AI to generate. They ask you which version do you like better. So they ask higher level questions, but they could ask, like, they give you the next word and they could give you a choice, and you could probably help them more if you do it adaptively, if you have some interaction in the process. But yeah, I don't know how much, I don't know, but yes, but it should be able to improve things.
One other question. So regarding this, so when you were trying to construct linear estimators, right, where linear convex combinations of two essentially histograms. So were you trying to minimize the empirical perplexity or the cross entropy term that you were speaking about what? I mean, are there analytical ways of doing this?
So we were looking at the perplexity on the validation data. But there's direct relation between the perplexity and the cross entropy, in the sense that if you look at the log of the perplexity is, as we said, is the cross entropy, and the difference is the KL divergence. So if you minimize the perplexity, you minimize your KL divergence from the actual distribution. It's the same.
So we can derive like analytical values for alpha 1 and alpha 2.
Yes. So the cross entropy is exactly, and this again we discussed with when you were on the break. The cross entropy is exactly the entropy plus the KL divergence between the two distributions. Yes. So if you minimize perplexity, you take the log, you minimize you minimize the cross entropy, and you minimize the entropy is fixed, even though you don't know it is fixed, you minimize the KL divergence. Does that make sense? Yeah.
Yeah.
And speaking
Alon, a quick question from me. Is some of this written up as a paper or something? I was trying to find it. I couldn't find.
Yeah. So yes. So we are we're late in writing this paper, but it will be out very soon. Yes, and we'll send you a copy.
If you're okay, if you could share the slides, that would be helpful too.
Sure. Okay. Cool.
Okay. Thanks a lot, Alon. Thank you.
Yeah, no, and just if in case if it's of interest, so you notice that when you came back, the cursor appeared, and just want to show you. Just a second. So if you sorry, if I go here, so while you're moving, we figured out how to do that, and if I share my whole screen, then you can see it's written here. So it says here to fix missing cursor, sharing key on the zoom, then go to the preferences, which is here. And all I needed to do was just was here to show pointer when using mouse or keypad pad. I think there was like a new version of Keynote, and when I installed that, I think this choice disappeared. So that was the issue.
Okay, cool.
All right.
Thanks a lot, Alon. Thanks for taking the time. It's wonderful.
Yeah, no, thank you. Thanks a lot.
Yeah.
Okay. Bye.
Bye-bye.
Bye.